Good morning, everyone. Today, I'm going to be teaching you how to use gas laws and stoichiometry. So we're going to be combining concepts from our last two units. You'll notice the notes for this are pretty straightforward. You're going to write a balanced equation. You're going to write down the information given to you in the problem. You're going to use the balanced equation to convert moles of one substance to moles of another substance, and then you're going to use the ideal gas law. So anytime we are performing stoichiometry, that just means we are going from one substance to another. And in this instance, since we're dealing with gases, we're going to be using the ideal gas law. So we're just going to jump right in and start some problems together. So this first problem says acetylene gas, also known as ethine, undergoes combustion to produce 3.35 moles of carbon dioxide. What volume of oxygen gas at STP is required for this reaction to occur? So the first thing we need to do is write a balanced equation. Well, before we can do that, we need to know what ethine is. So if you remember from our organic chemistry lessons, eth means two carbons. Ine means those two carbons are joined together by a triple bond. And then you have a hydrogen on each carbon as well. So the formula for that is C2H2. Now, this is a combustion reaction, so you also have to recall what that means. This is a hydrocarbon that we are burning, we are combusting. So we have to have oxygen as our other reactant, and we also are producing CO2 plus H2O. Now you may also recall that combustion reactions can be difficult to balance. So I like to look ahead before I write anything down. For instance, I have two carbons. So on this side, I could put a 2, and I have two hydrogens, so that's already balanced. But if I put a 2 in front of this carbon, that's 4 plus 1, that's 5 oxygens, which is an odd number. And I cannot make this an odd number. So I can go ahead and see that I'm going to have to double everything. So I'm going to put a 2 in front of ethine. That gives me 4 carbons. So I'll put a 4 in front of this carbon. 2 times 2 hydrogens gives me 4. So I'm going to put a 2 in front of water. Now I have 4 hydrogens. And then for my oxygens, 4 times 2 is 8, plus 2 is 10. So I need a 5 in front of my oxygen. All right, so now the equation is balanced. So now I'm supposed to write down the information given in the problem under the corresponding formula. So they are telling me that after you combust acetylene gas, you produce 3.35 moles of carbon dioxide. So 3.35 moles. I'm going to write that there. And we're supposed to be solving for the volume of oxygen gas. So I'm going to put a question mark under oxygen, and I'm going to put liters next to that. Now, you can't just simply go from moles to liters by doing stoichiometry. This is where ideal gas law comes in. So ideal gas law is going to be our key to go from moles to liters, but our key from going one formula to the next is going to be stoichiometry. And it's really up to you which one you want to do first. I'm going to go ahead and do the stoichiometry part. So I'm going to start with 3.35 moles of CO2. I'm going to move moles of CO2 on the bottom. Moles of oxygen goes on top. So now I'm setting up my mole to mole ratio. Notice I didn't have to convert anything grams to moles because it's already in moles. So I can go straight into my ratio. So that's a 5-to-4 ratio. And when I multiply that, 3.35 times 5 divided by 4, I get 4.18, 4.19 after I round. All right. So now what I have is moles of oxygen. I want it to be in liters. So this is where you need to use ideal gas law. So that's PV equals nRT. So for our pressure, it's standard temperature and pressure. So that's 1 atmosphere. We don't know the volume. Our moles, we just solved for 4.19 moles. R is 0.0821. And then standard temperature is 273 Kelvin. So I'm going to multiply those together. Sorry, you can't see that. 4.19 times 0.0821 times 273. And I get 93.9. And I mean, you could divide it by 1, but you're still going to get 93.9 liters of oxygen. And we're done. Now, I'm going to throw another little curveball at you. There is a thing known as standard molar volume. Now, standard molar volume says that at STP, 22.4 liters is equal to 1 mole. Okay? So since that's the case, like for instance, this problem is at STP. Where they're getting that number from, that's what you get when you multiply 0.0821 times 273. If you multiply those two numbers, you get 22.4. So to save you some time, if you ever have a problem where you need to use ideal gas law and the conditions are at STP, you could just take your number in moles, 4.19 moles, move moles to the bottom, liters on top, and you can use the standard molar volume. So I put 22.4 on top and 1 on the bottom, multiply those together, and you still get 93.9. Now, if that's confusing to you, forget I said it, because you're going to get the same thing either way. This is just a shortcut to save you some time. Again, though, you can only use the standard molar volume when the conditions are at STP. Okay, hopefully that made sense. We're going to move on to problem number 2. And it says, when 2.85 grams of zinc reacts with 3.16 grams of hydrochloric acid, how many milliliters of gas will be produced at STP? Okay, so let's start with a balanced equation. Zinc is reacting with hydrochloric acid. This is a single replacement reaction. Zinc replaces hydrogen, which is a diatomic molecule. Zinc is now with chlorine, and don't forget to cross that 2. So then we put a 2 in front of HCl. So now let's write down what we know. We have 2.85 grams of zinc, and we have 3.16 grams of hydrochloric acid. How many milliliters of gas? Now, this might have been easier if we could actually do these reactions together. But if you were to take the time to write out the net ionic equation, you would see that the net product for this reaction is hydrogen gas. If you put some zinc and some hydrochloric acid, that hydrochloric acid is going to immediately eat away at the zinc, producing gas bubbles. You'll see those gas bubbles coming out of solution. So when they say how many milliliters of gas will be produced, they're assuming you know that of these two options, this is the gas. Okay. Now this problem's a little bit different. It's a little bit different because they didn't give you the amount of just one thing. They gave you the amounts of both of your reactants. So there should be a bell ringing in your head right now, hopefully. that tells you whenever you're given the amount of both reactants and you're supposed to solve for the amount of product that would be produced, you have to find the limiting reactant. So that's what we're going to do next. We need to figure out which one of these is the limiting. That will help us determine the theoretical yield of hydrogen gas. So for zinc, I have 2.85 grams. Now, before I can go into a mole ratio, it's in grams. It needs to be in moles first. So I'm going to move grams to the bottom, moles on top. One goes next to mole, and now I need the molar mass of zinc. So I just so happen to have my periodic table in the background. So it's 65.38. And now I'll set up my ratio. I'm moving moles of zinc to the bottom, and I'm putting moles of hydrogen on the top. Now, I know in times past, let's go ahead and put that ratio. That's 1 to 1. Okay. So I know in times past, we have not stopped here. We typically now convert that into grams. But in this case, that would be a useless step because we want to figure out which one of these reactants is the limiting, and we want to solve for moles of product so that we can plug it into our ideal gas law equation and convert it to milliliters. All right, so because of that, I'm going to stop right there. So in my calculator, I'm going to type in 2.85 divided by 65.38. It's a 1 to 1 ratio, so I can go ahead and press equals. And I get 0.0436. Moles of hydrogen. All right, I'm not done. I got to do the same thing for hydrochloric acid. So it's 3.16 grams of HCl. I move grams to the bottom, moles on top. And now I've got to find the molar mass of HCl. I'll do that over here. So I have 1 hydrogen. Hydrogen's mass is 1.01. Chlorine's mass is 35.45. And I should be finished with my periodic table for now. So I'm going to turn that back to widescreen. Okay, so add those two together. I get 36.46. And now for my ratio, I move moles of HCl to the bottom. I put moles of hydrogen gas on top. That ratio is 1 to 2. So 3.16 divided by 36.46 divided by 2. And I get 0.0433. So you can see this is close. But even so, hydrochloric acid ends up being the limiting reactant in this case. It produces less product. So this is the one we're going to go with. This is our theoretical yield. Well, we're not done because remember the point is we're supposed to convert it into milliliters. So you have some options. Remember, this is an STP, so you could just use the standard molar volume. You could just go out to the side, drop moles to the bottom, put liters on top, and that would be 22.4 over 1. So 0.0433 times 22.4, and that would round to 0.970. That's in liters, so in milliliters, that would be 970 milliliters. I put a decimal at the end to keep my 3 sig figs. So that's option 1. Another option you have is plugging that into ideal gas law. So for PV equals nRT, your P is 1, your volume you don't know, N is 0.0433, 0.0821, 273, and then solve for V. I'm going to save myself some time. You get the same thing. So you get 970, well, sorry, you get 0.970 liters. Because remember, anytime we use ideal gas law, the volume is going to come out in liters. And then you just move your decimal to the right 3 places to put it in milliliters. Okay. So again, hopefully that wasn't too confusing. If it was, I'd encourage you to rewind, go back through the problem again. But we're going to move on to problem number 3. All right, this says if 29 liters of methane undergoes complete combustion at 0.961 atmospheres and 140 degrees Celsius, how many moles of water vapor would be produced? So again, start with a balanced equation. Methane, meth means 1 carbon, and then you've got those 4 hydrogens around it. So that's CH4 plus O2, this is a combustion reaction, yields CO2 plus H2O. They're assuming you know what combustion means, so they didn't take the time to tell you what the rest of the equation looks like. Now we have to balance it. So 1 carbon, 1 carbon, 4 hydrogens, 2 hydrogens. Let's fix that. Now I have 2 plus 2, so I have 4 oxygens, so I'm going to put a 2 in front of oxygen here. So now the equation is balanced. So what have they told me? They've given me the liters of methane, and they've asked me to solve for moles of water vapor. So again, it really doesn't matter what you do first, if you want to do your stoichiometry first, or if you want to convert it into moles first using the ideal gas law. I'll go ahead and use my ideal gas law to get it into moles, and then I'll do my stoichiometry. So PV equals nRT. I can't use standard molar volume here because it's not a STP. So my pressure is 0.961 atmospheres. My volume is 29. I don't know my moles. I know that R is 0.0821. And then I've got to add 273 to my temperature, and I get 413 Kelvin. So don't forget, ideal gas law is the law that everything has to be in a particular unit. All right, I need to get N by itself, so I'm going to divide both sides by 0.0821 and by 413. So those cancel. Let's see what we get. 0.961 times 29 divided by 0.0821 divided by 413. And to 3 sig figs, I get 0.822. Moles of methane. That's not the answer, because that's moles of methane. I want to know how many moles of water vapor that is. So I'll go ahead and do that now. I'm going to move moles of methane to the bottom. Moles of water vapor goes on top. And that is a 2-to-1 ratio. So I end up having to multiply by 2. 0.822 times 2 gives me 1.64 moles of water. Okay. So again, hope that made sense. We're going to move on to our last problem. Methanol is made by reacting 0.45 liters of carbon monoxide and 0.82 liters of hydrogen gas at 4.5 atmospheres and 362 degrees Celsius. You have several questions to answer here. The first one is, which reactant is the limiting? Well, this is a problem where they've given you the amount of both reactants, so it makes sense that we would have to solve for the limiting. Let's first write a balanced equation. Methanol. Meth is one carbon. All means there's a hydroxyl group attached. So it looks something like this. So that's going to be C. You can write it CH3OH. You can write it CH4O. I'm going to write it CH3OH just because that's the more common way that looks. All right, so methanol is made by reacting carbon monoxide and hydrogen gas. So that's actually my product. Carbon monoxide, hydrogen gas are my reactants. So let's see if it's balanced. Carbon and oxygen are balanced. Hydrogen is not. There's 4 on the right, 2 on the left. So I'm going to put a 2 here. Now the equation is balanced, and I'm going to write the amounts that they've given me. So under carbon monoxide, I've got 0.45 liters. Under hydrogen gas, I've got 0.82 liters. And eventually, I am going to have to solve for methanol. But the first thing I need to do is figure out which one of these is my limiting. Now, something I haven't said yet, you don't have to convert these into moles in order to do a ratio. Okay, I know we had to do that for grams. Like, you can't just go into a ratio with grams. You do have to convert to moles first. But for liters, you can just leave it as liters and go straight into your ratio. So 0.45 liters of carbon monoxide. Liters goes on bottom. CO, CH3OH, and the ratio is 1:1. So I still get 0.45 liters. Right, do the same thing for your other reactant. 0.82 liters of hydrogen. Put my product on top, hydrogen on the bottom. That ratio is 1:2. So I end up getting 0.41 liters of CH3OH. So you can see that this is the smaller amount, meaning that hydrogen gas is our limiting reactant. All right, question number 2. How much of the excess reagent remains? All right, well, you have to start with the limiting. The limiting is hydrogen gas. I'm going to move liters of hydrogen to the bottom. I'm going to put my excess reactant on top. That ratio is 1:2. So I get 0.41 liters of CO. That's how much was used. How much remains is determined when I subtract that number from the original amount. And the original amount of CO was 0.45. So 0.04 liters of CO remains. Now, we kind of lucked out here because this question wasn't specific about what unit they wanted that in. If they had said how much remains in grams, then we'd have more work to do. We would have to plug that number into ideal gas law, solve for moles, and then multiply by the molar mass of carbon monoxide to get it into grams. But again, we sort of lucked out because they didn't specify. So I think that's good enough. All right, letter C. It says, what volume of methanol is produced assuming the same temperature and pressure? They're basically asking you what is the theoretical yield of methanol. And remember, that is determined by the limiting reactant. So since the limiting reactant produced this much methanol, that is the answer, 0.41 liters. And again, they asked for the volume. It's in liters. We never converted it, so we are done with that problem. All right, and that, my friends, finishes off Unit 8. We are done with gas laws. Obviously, you still have more practice problems to do, and I believe you might have a quiz. I can't remember. But either way, Let me know if you have any questions.